Hi folks, we are on to our third video for class on Thursday, November 6th, and this particular video is going to be a continuation of the lecture notes on the two-way analysis of variance, or Factorial ANOVA. And where we ended off last time in the lecture was on talking about the different hypotheses of a two-way ANOVA and the different way that these hypotheses in terms of main effects and interaction effects would look graphed from both the null hypothesis standpoint and the alternative hypothesis standpoint. So this was the last slide that we talked about in class. We're going to kind of continue with that and talk a little bit about actually then testing the hypothesis itself statistically and how that works. Okay, so for hypothesis testing with the two-way or the Factorial ANOVA, we're actually going to have the three different hypotheses. So recall that we have a hypothesis for the main effect of the first independent variable. In this example that we've been using in class, it's that the main effect of gender on attractiveness ratings of the pictures. We have a second hypothesis that's about the main effect for humor on attractiveness ratings, and then we have a third hypothesis that there will be the null hypothesis that there's no interaction between humor and gender. So with three different hypotheses, we're going to have three different F ratios. So we're actually testing three, so we have to calculate three F ratios to test. The first two are going to be the main effects. So the numerator, or the number that goes at the top of our hypothesis test, is going to be the variability between the rows. And for example, that's humor. In the second one, we're going to have the numerator as the variability between the column totals, so that's gender. And then the final one is the numerator for the remaining, the numerator will be the remaining variability, which is the interaction between humor and gender. So these three numerators then are three different between subjects effects. So for this example, if you want to compare it to a one-way ANOVA, where we have the between subjects divided by within subjects in order to get our F ratio, for this we actually have, again, it's a between subjects divided by within subjects design, but we actually have three different between subjects comparisons. So in each of these, the numerator, or the top number in the F ratio, is going to come as a variability between the humor groups for number one, between the genders for number two, and then the interaction, so all remaining variability between humor and gender in number three. And so for all of these examples, then you know what the bottom number is going to be. The denominator is going to be our within subjects variability, so the variability within any cell, okay, within the conditions themselves. So these are going to be within the cells variability as our denominator. So number 1, 2, and 3 are going to be our effects, and the denominator is our error, effects divided by error, in order to calculate our F ratio. So this is it's a little bit of a blurry table, but I want you to take a look at it on your computer screen in the lecture notes, because this basically gives some directions in how you're going to calculate the F ratios. Okay, so we have four sums of squares in a Factorial ANOVA. We have the three between subjects, and that's the row, so sums of square rows. We have a column, the sums of square columns, and we have the interaction, sums of square interaction. So these three are the between subjects, and then the final is the within subjects, or within cells, sums of squares. So when you add all of these together, it equals your total sums of squares. All right? And then, of course, we're going to have variance estimates, or our mean squares. And again, just like with the one factor ANOVA, we have between subjects mean squares and within subjects mean squares. It's just that in a factorial ANOVA, our between subjects mean squares is divided between row column, and interaction, and then we have our mean squares within cells. Okay, so we calculate the F ratio the same way in a factorial ANOVA that we just did in a one-way ANOVA. And you can kind of read the arrows here a little bit. So for the row, we're going to have, that's the main effect of the variable on the row. We are going to take our mean square row and divide it by our mean square within. All right, so between divided by within, same thing we've been doing, and that gives us our F ratio for our first independent variable, or our main effect on our row. For our column, for our second independent variable, we take our mean square for our column and divide it by mean squares within. You can see that that arrow goes up. So you have between divided by within, and that's going to give you the main effect for the second independent variable. And then for interaction, we take our mean squares interaction, divide it by our mean squares within, and that gives us our interaction F ratio. So you can see that we have, we're working with familiar ideas, but they're going to be more calculations without a doubt with a factorial ANOVA. I'm going to lead you through that in a moment. I want you to kind of follow along and see how we would actually calculate that. And first, so that you have it in your notes, I want to talk about calculating sums of squares and degrees of freedom for this particular type of ANOVA. All right, so as always, our variance is sums of squares divided by degrees of freedom. Okay. So as I've just said, I wanted this to be in your notes. I've said it already verbally. Our sums of squares total represents how far each individual score is from the grand mean, or where the grand mean is the mean of all the scores that are included in the entire experiment. So that's our sums of square total, and that's what it represents. Sums of square between, as I said, is divided into three different categories, but remember that sums of square between is how far the cell means are from the grand mean, and we look at that by row, by column, and by interaction, which is going to be the total sums of square minus the row and the column. And so sums of squares between, remember, is our effect. We think that's variability or differences in the mean scores that are due to the independent variable and not to error. Error is our sums of square within. That's how far apart each score is from its own group mean. So that's within cells or within subjects variability. Random variability is another way that we've talked about in class, just the fact that there are individual differences, and sometimes people are going to rate a subject as more or less attractive, and it has nothing to do with being funny or male or female, just that people are different. And so we want to control for just this inherent kind of random difference with sums of square within. All right, so now let's talk about degrees of freedom for this test. So as you can imagine, we actually have quite a few different degrees of freedom, since we have several different calculations that we're doing. All right, the easy one here, degrees of freedom total. We're familiar with this. So the total degrees of freedom for a factorial ANOVA is n minus 1, where n is the number of subjects in the total experiment, so the grand N. All the cells added together. So n minus 1 is degrees of free total. Right. Degrees of freedom between is going to equal the number of cells in your table minus 1. Okay. That's a little less meaningful in the calculation. It's just something to kind of keep in mind, that it's the number of cells minus 1, because it can give you a checkpoint for your degrees of freedom row, your degrees of freedom column, and your degrees of freedom interaction, which are really the more useful ones that we're actually going to use in the calculation. So let's start with degrees of freedom row. To calculate the degrees of freedom for our row, our first main effect, the symbol for that is r minus 1, where r means the number of rows. Okay? So if you have two factors in your independent variable, then you're going to have 2 rows. So the degrees of freedom row is going to be 2 minus 1. If you have 3 groups of your independent variable, your first independent variable in your row, then you're going to have 3 rows, and it's going to be 3 minus 1, so 2 degrees of freedom for rows. All right. The same calculation is done for degrees of freedom column. Remember, that's just your second independent variable, and that's going to be C minus 1, where C equals the number of columns. So if you have 2 groups in your second independent variable, it will be 2 columns minus 1, so degrees of freedom would be 1. If you have 3 groups in your second independent variable, it will be 3 minus 1, 3 columns minus 1, so degrees of freedom would be 2 in that case. All right, and then we have our final degrees of freedom between, which we're going to calculate this way. The interaction is going to be your degrees of freedom row times your degrees of freedom column. All right, so once you have your degrees of freedom for your row and your degrees of freedom for column, you're just going to multiply them together to get your degrees of freedom for your interaction. Okay, finally, we have one last degrees of freedom. I bet you can guess what it's for. Within. So we have a total, we have a between, now we need a within. We need that error degrees of freedom. Okay, so take a look at this with me. Degrees of freedom within is calculated by the number of rows times the number of columns times n minus 1. And n is something a little different here, so let's memorize this and not be confused. N for degrees of freedom within is the number of raw scores per cell, okay? So if you had, well, I'll show you the example in a moment and it'll make a little bit more sense. So it's the number of raw scores per cell. So it's the number of rows times the number of columns times n minus 1, where n equals the number of raw scores per cell. All right. So I'm going to show you some formulas now, and these are going to be for row, column, main effects, and interaction effects, and then finally for getting the sums of squares within. I don't have to tell you how to do sums of squares total, because once you calculate the 4 sums of squares, the 3 between, and the 1 within, you can just add them together and get your total sums of squares. I think your book gives you a calculation for sums of squares total, and you may be asked to do that in the homework, so you might want to check in and be familiar with that. But for class, in terms of calculation, I think it just makes more sense to calculate the sums of squares that we're actually interested in, that we're gonna do something with, and then we can add them together to get the total. Okay, so the formula for our row main effects, our first independent variable main effects, is as follows. We have sums of square rows is going to equal this entire value together, and how you read this is, this says row 1, the sum of x of row 1 squared, plus the sum of x for row 2 squared, plus, and what this says is the sum of x to row r, which just means you keep doing this until you include all of your rows in this calculation. If you only have 2 rows, then you'll only have these 2 figures. If you have 3 rows, then you'll have a third figure here. If you have 4 rows, then you'll include a fourth. You'll have row 4 sum of x squared. Okay, and then you're going to divide that entire value by n row, which means the number of total people in the entire row. So it's going to be this n plus this n plus this n. Okay, so in the cell plus the cell plus the cell. And then we're going to, once we've calculated that, we're going to subtract from this total the grand sum of x, so summing x's of all of the cells that we have in the entire calculation. Then we're going to square that and divide it by n, where n is the total number of people in the entire experiment. Remember that degrees of freedom for rows is the number of rows, r minus 1. And then to calculate the mean square for rows, we're going to take sum of squares rows over degrees of freedom rows. This is very familiar. This is no different than what we've been doing for ANOVA. And then f obtained, again, the same thing. We're going to take our mean squares rows and divide it by mean squares within cells. All right, so we're going to now look at the column main effects, and it is identical. The formula is identical. You're just, instead of noting row 1, row 2, row 3, okay, instead you're looking at column 1, column 2, up to as many columns as you have. So you get the sum of x, and then square that, add those together, and divide by the number, the n in the column total. Okay, so the number here plus the number here plus the number here. Then from that, again, you're going to subtract the same figure that you subtracted for formula for the row formula, main effect formula. So the grand sum of x, square it, divided by total n. Okay, total number of people in your experiment. Degrees of freedom columns is c minus 1, number of columns minus 1, and then you're going to calculate your mean squares and your f obtained for columns the same way. Okay. Now let's look at a different one. This looks a little bit different, and this is the final between subjects formulation for sum of squares. So to get our sum of squares for the interaction, we're going to now be working in the cells, so not in rows or columns, but in the individual cells. So how do you read this formula? This is saying cell 1, cell row 1, column 1. Okay, so this is denoting that this is the cell of row 1, column 1. You're going to take the sum of x of that cell, square it. Okay, plus this says cell row 1, column 2. And you're going to take the sum of x squared. And basically you're going to keep doing that until you have all of the cells, all the cells that are included in your experiment, the sum of x squared added. And then you're going to divide that by the number of participants that are included in each cell. Okay, you're going to take that entire value, and then you're going to subtract three things now. You're going to subtract the same grand sum of x squared over n, but you're also going to get rid of the sums of squares from the rows and columns that you've already done. So you're going to also subtract the sums of square rows and the sums of square columns that you've just calculated in addition. So basically it's everything that's left over after the rows and the columns is going to be your sums of squares interaction. The degrees of freedom, if you recall, is the number of rows minus 1 times the number of columns minus 1. And so we calculate the mean squares of the interaction by taking sums of squares interaction divided by degrees of freedom, and then get our f obtained by our mean squares interaction, which is our final between groups variable, and divide that by ms within. Alright, so we have one more calculation we need to do, and that is mean squares within. So for this particular, for mean squares within, you're going to notice that again it looks a lot like the ANOVA, the one-way ANOVA calculation. So what you first need to do for your sums of square within is you need to calculate your grand sum of x squared. So here, in terms of your notation, you have all of your raw data squared, and then you sum all the squares together, and that's your grand sum of x squared. And from that value, you're going to subtract this value here, which you've actually just calculated in your interaction effect. So this is the same as that first figure in the interaction effect. Look here, okay, as this interaction. So you've just calculated it, and you're going to subtract those cell sum of x from the grand sum of x squared for your within cell formula. Right? Your within cell sum of degrees of freedom is going to be the number of rows times the number of columns times the number per cell minus 1. And then you're going to calculate your mean squares within by dividing your sums of square within by your degrees of freedom. So the same pattern. Okay. So let's look at our attractiveness data again. Here is what we've been working with in class, where we have our rows, here's a row and here's a row. So we have our row variable is going to be humor, because That's what we are going to read in our row. And you can see that we have our row means calculated so as to begin the calculation for funny and then for not funny. So this calculation are all of these raw scores for funny, and adding them all together and getting the mean for all funny regardless of gender. And this is the mean for adding all 6 of these scores regardless of gender to get an average not funny score. So that's going to allow us to look at row effects, which is humor. Then we have column. So gender is our column, and we read this down. Here's our male column, and so we have 6 males who participated, and we can get their average attraction score just by male, regardless of how funny or not funny the picture was. And this is our female. We have 6 female in this column, and here's our average attractiveness rating for the female raters. Okay, so those are our column effects here. All right, now I'm going to switch out of this and start to look a little bit at how we would calculate this. First, here's what the source table looks like. Okay, you can see we're adding a little bit to it. We have 3 between subjects, sums of squares, 1 within, and then the total. We have 3 between subjects degrees of freedom, 1 within, and then the total. Then we have 4 mean squares calculations, and 3 F obtained. And I went ahead and just actually added an F crit to the source table so that you could have a quick kind of glance about whether your F obtained was was equal to or greater than your F crit. So I just added that in. So let me show you the worksheet about how this is calculated.